and then pin my video. And let's see. I know one thing that I've been missing is I haven't been watching the chat stream. So if you chat something, I'm trying to pay closer attention to that now to answer any questions. So let me share this one, right? Where is it? Where did it go? Zoom, zoom, zoom. Huh. Well, let me try something else. Maybe I need to do, no. Let's go back to a Zoom session. Try that again. Share. There it is. Okay. Now. All right. So I'm going to back up one slide so we can sort of make connections with chapter 3 where we left off. I think the last topic covered was percent composition of a compound. And the mass percent of any element in a compound is easily determined either from the bench, from the data. If you know the mass of the element in the compound and the mass of the compound, you can calculate the mass percent. And in fact, we did that in Excel in that first lab. That's one of the things that we did, the mass percent of sodium carbonate in the sample. Well, it wasn't exactly the same, it was similar. It was the percent of the compound in the ore, but the math is exactly the same. You have one component, the mass of one component, and then the total mass divided into it times 100 is the percent. So if you have the formula of the compound, then you can do a calculation, we call it a theoretical composition. What's the ideal composition of, say, iron in iron 3 oxide? We have the formula here, Fe2O3. So all we need is the molar masses of each of the elements in the compound. And this one is 5585 is the molar mass. We left out the moles because all the moles cancel anyway. So many grams. Well, let's just say theoretically, we have 1 mole of the compound. Okay, so if we have 1 mole of the compound, we've already shown how to calculate the molar mass of the compound. You need the molar mass of iron times 2, molar mass of oxygen times 3, add those together. That's your denominator. And then the numerator is the element of interest, in this case, iron. And since there are 2 irons, for every 1 mole of the compound, you need 2 times the molar mass. So after that, that's the thinking part. The rest of it is crunching numbers. You find 2 times the molar mass of iron divided by the molar mass of the compound, which always includes the numerator component. It's always in both the numerator and the denominator. Then plus whatever else is not included in the numerator, and the rest of the compound is in the denominator. And in this case, we calculate the ideal percent of iron in this compound as 69.94%. Okay, so now we can get on with a sample problem. So let's say we have a 100-gram sample of each of the following, and this is sort of on the tails of a previous example in one of the earlier slides. 100-gram sample of each one of these, and we want to rank them from highest to lowest percent oxygen by mass. So what you need to know is you have to set up your assembly line. Remember? I don't want to take up too much time doing that, but I'll just call your attention to the last time we used an assembly line, and you set up each one of the compounds. I like to put them in a vertical, each one of these compounds, and then you do the calculation for one, and you duplicate that calculation with the appropriate changes for each one. And you just string them out across the page or across the board. And let's do one of them. We'll do water. Right, so if we have water, then the percent composition of oxygen by mass in water will be oxygen, and we only have one of them, but we also have oxygen in the total. So there we have oxygen, there we have oxygen plus the hydrogen times 100. And just to be thorough, and let's see, I did something wrong. Hold on a second. Let me back up. And then, yeah, there we go. So I get 8879. Percent oxygen in that compound. And you can do that for each one of them. Just right on down the line, simple calculation, and then compare the percent compositions and put them in order. So as it turns out, water has the highest percent oxygen in all these compounds. And when you think about it logically, that makes sense. Look at what's part of each of the other compounds. Here we have what you might think is a lot of oxygen in this one, but you also have carbon. So carbon dioxide is probably close, but somewhat less than water. And then for propionic acid, you have carbon and hydrogen both in large amounts, and here you have 2 nitrogens in addition to the oxygen. Nitrogens are 14, so that's 28 against 16. So, and all oxygen has to balance in its total is these 2 protons, and they're practically nothing. That's why the percent composition is so high for water. And you just compare them. Do your assembly line, compare the values, and you're done. Now, this is more important, I think. Okay. My board's going to be difficult today. Let's see. All right. We're going to have to get aggressive. There we go. All right. Now the upcoming problem is one that gives some students trouble, especially if you're not very methodical about the approach. So let me stretch out. I'm going to need a little bit more room. Let me stretch this board out some. And where am I? I'll be sure it's, nope. There we go. So everything's on the, is in the frame. All right, so first, definitions. The difference between empirical formula and molecular formula. If you start with molecular formula, it makes sense. In other words, the molecular formula is actually how many atoms of each element are in the molecule. So water would be 2 hydrogens, 1 oxygen. Carbon dioxide would be 1 carbon, 2 oxygens, and so forth. That represents that unit, the compound unit. The empirical formula is a simplification of the molecular formula. And if you have a compound that can be reduced to a simpler whole number ratio, then that's what you do to obtain the empirical formula. For instance, I'm going to write it on this side over here because it probably erase better. If you have something like that's the molecular formula for benzene. But it is possible to, a divisor of 6 will reduce that to an empirical formula of CH. Okay. Now, the empirical formula is not the end game. It's an intermediate stage in the process that I'm going to show you. Because CH could just as easily be acetylene. Okay, so the empirical formula is useful, but it's not the end game for us. So what do I mean by that? All right. You know what? Give me just a second. I don't like the way that board's acting, so I'm going to put another one up there and see if it works better. Let me just try it to see. Much better. Okay, now we can proceed. So you need to get firmly in mind the difference between empirical formula and molecular formula. Empirical formula is the simplest whole number ratio of elements in a compound. So if our compound had an even odd type arrangement where we had maybe 3 carbons and 8 hydrogens, that could not be reduced any further because you can't divide 3 and 8 by any number that will give you a simpler value. So on some occasions, the empirical formula and the molecular formula are identical. But in the process I'm going to show you coming up next, you don't know that until you've gone through the process all the way through empirical formula and to molecular formula. Then you can make the statement that they're both equal or not. All right, so that's enough of that. Let's, this is sort of an intermediate. How do we know the composition of compounds? Well, if the compounds are hydrocarbons or carbohydrates, which is carbon, hydrogen, oxygen, hydrocarbons are carbon and hydrogen only, you can use this type of arrangement And I've used one of these before. Your sample goes in here, and it's in a furnace, so it's very hot, and you introduce oxygen, which converts all the carbon-containing compounds and hydrogen-containing compounds into either carbon dioxide or water. And then you have traps that are, you weigh them first before you set up your the train. And then when the gas products are blown out of your sample, the hydrogen containing part, or the water, which is the conversion of hydrogen, is absorbed in magnesium chlorate. And then when you're finished combusting the sample, you just detach everything and weigh and get a difference. So you know the difference is due to water. Same thing for the carbon train. This is sodium hydroxide, or it could be it could be lithium hydroxide, which is more expensive. It could be potassium hydroxide. Any of the hydroxides will work, and they will absorb carbon dioxide, and you get the weight by difference there. So that's one way to get the actual percent values for at least carbon and hydrogen. And then there are other absorbents that can be used for things like sulfur, which is a major component of many organic molecules or biochemicals. So that's just to show you that it's not, I didn't just pull it fully formed out of my head. It actually happens. Let's see. Okay, so here's a sample problem, and this is probably the best way to show you the procedure. We have analyzed a sample that we know is pure, called adipic acid. It's one of the fatty acids. And we get this information. We know that the sample is composed of 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen. And you can satisfy yourself that these are the only components by just adding those up, and it should be very close to 100%. Now that is done by probably that combustion train that I just showed you would be a good way to analyze this one. And if you know by other means that it has carbon, hydrogen, oxygen only, and you can do qualitative tests to determine that fact. Then if you know carbon and hydrogen by that combustion train, then the difference is going to be oxygen. So that's done by one set of analyses. A completely separate set of analyses will give you the actual molar mass of the compound, which in this case is 146 grams per mole. Right? And if you stick around for second semester, we'll show you some ways to get this value. And I'll give you a hint. We use colligative properties. So the first thing you do is use this percent composition data to determine the empirical formula, the simplest whole number ratio of elements in the compound. Then the step after that is you use the actual molar mass to determine what the molecular formula is. Okay, so I'll show you how that goes. Here we have carbon, hydrogen, oxygen. So this is a perfect setup for Henry Ford. Set up your assembly line. Carbon at 49.3%. Here's carbon. Okay, hydrogen and oxygen. And hydrogen is 6.9%. And 43.8% oxygen. All right. You have to ask yourself this question. What do we need to know in order to write an empirical formula? You need to know the ratio of atoms, right? And percent doesn't give you that. This is percent by mass, right? And you can't get that. You can't do the ratio based on those percent values. You need to know the ratio of atoms, or the ratio of moles is equally as useful, because when you write a compound, right, we want these values down here. And this can either be number of atoms in the molecule or number of moles of each in a mole of the compound. Both are equally valid. And since we're talking about the macro world, we're going to go with moles. It's easier to handle. Okay, so what do we do with percent? If we want to convert something to moles, we need to know its mass, don't we? Because molar mass is our conversion factor to moles. So we need to know the masses that are represented here. The simplest way to do that is to assume that you have 100 grams of your sample. Right? You don't have to have 100 grams, but for calculation purposes, these are ratioed to one another. So if you have 100 gram of sample, it doesn't matter if it's 100 or 50 or 1,000 grams, you're still going to get the same ratio. So the simplest way is to go to 100 grams. Why? What does percent mean? Percent means parts per 100. So if you have 100 grams, the percent value is exactly that many grams, right? So the first assumption is that you have a 100 gram sample. Now we have 49.3 grams of carbon, 6.9 grams of hydrogen, and 43.8 grams of oxygen. Now we can convert to moles, right? So assembly line, got to cancel grams, so it has to be on the bottom, and moles on the top. Right? So what value goes in here? How many grams per mole is carbon? Look it up on your periodic table, and to 2 decimal places, it's 12.01. Okay. Hydrogen to 2 decimal places is 1.01. And oxygen rounded to 2 decimal places is 16. Okay. Now we can find out how many moles these masses represent and start ratioing them to the nearest whole number. So 49.3, 12.01 divided into it gives us 4.105. Notice I kept an extra digit. Right? There are only 3 significant figures here. I kept 4. Why? Because when you've got a series of calculations to do, you don't want to throw away any of your digits yet. We'll do that rounding at the end. If you keep more of your digits here that are offered by your calculator, then the error at the end is much less than if you round each time. So we're going to keep those digits. 6.9 divided by 1.01 is 6.832. Okay, and the last one, 43.8 for oxygen divided by 16 is 2.738. Okay, now this is moles. Now we have a mole ratio for our compound. but you never see compounds written with decimal amounts as their subscripts. They're always whole numbers, which makes sense because, I mean, how can you bond a fraction of an atom, right? So we need to reduce these to the simplest whole number ratio, which is going to be our empirical formula. So the easiest way to do this is, now that this ratio is established, this is firm. So anything we do to one, if we do the same thing to the other one, we haven't changed the ratio. So if we divide this one by 2.738, we get 1. And we divide this one by that number and divide this one by that number, we still have the same ratio of each one. Right? So if we divide by 2.738 and divide each one by that same number, then we get 1 for this one. And we go back, let's see, let me see if I can do this. 6382, divide by 2.738. Yeah, this is about 2.5. Now I'm going to round at this point because we're headed toward whole number ratios. So rounding like that is a good thing. 4.105 there, and 2.738 divide, this is 1.5. There we go. We're getting closer. We're inching closer to a whole number ratio. So, what do we need to do to make whole numbers out of this? If you multiply all of them through by 2, you get rid of the half, right? 2 times a half is 1. So if we multiply 2 times each one of these, then we get 3, 5, 2. Now you have to ask yourself, is that the simplest whole number ratio? Well, probably, because that's an even number, and those are both odds. Not only are they odds, they're all prime numbers. So nothing else is going to divide into them but themselves and 1. So that's our whole number ratio of carbon, hydrogen, and oxygen. That's our empirical formula. C3H5O2, simplest whole number ratio. But we don't know yet if that is the molecular formula. So how do we get that? Now, here's where we use the 146 grams per mole. We know that this value is the molar mass. And if we were to find the molar mass of this, and it's equal to that, then we know that we're already home. So let's find out what the molar mass of this formula is. I like to call it the empirical mass rather than the molar mass. So the empirical mass of that one would be 12.01 times 3, right? For carbon. Hydrogen would be 5 times 1.05, 5.05. And then oxygen is 2 times 16, which is 32. So this one is 73.08. All right. So that's not the molecular formula, right? Because it does not equal 146 grams. But look what we're looking for is a value here that we can multiply times each one of these, right? If this is the simplest whole number ratio, then we theoretically could have gotten there by dividing the actual ratio by some whole number, which is x. We're just going backwards. We're going to find out what x is so we can convert the empirical back to the molecular. So our multiplier here is the target. if we multiplied, let's just say it can't be 1, right, because that doesn't give us the right value. 146, right here. That's where we're headed. What if we multiply by 2? 2 times each one of these would double that value as well, would it not? So if we multiply each one of these by 2 and multiply that times 2, what do we get? 146. So x is equal to 2 because of the ratio of this one to this one. Now that's one way to look at it. If it's not as obvious as this, then what you can do is take this, divide it by that. And that gives you the x value. Okay, so you can either reason it out, you know, say x equals 2, what happens? X equals 3, what happens? X equals 4, or you can just ratio the 2 and calculate the x. Now, very often that value will come out to some fraction. Let's just say it came out to 2.168. You would round it to the nearest whole number. If it came out to 2.54, then you would have a pickle, because which way do you go, up or down? I know the rounding rules say if it's 5, you go up. But what you would have to do then was round down, try that one, round up, and try that one, and see which one is closer. And I intend not to give you any problems like that. That's just a waste of time and effort. But it is a real possibility if you were to do this in the lab, and we're trying to determine the formula, then that's a real possibility. And one of the main problems, well, experimental error is probably why that would not come out exactly where you want it to be. Okay, any questions before we move on? It's a very simple process. You just have to be methodical about it. Work your way through empirical, then go to molecular. Yeah, that was starting to be difficult too. Let's see. The rule in using cleaning products is use the least aggressive one first. So I'll start with water. That's close enough. Okay, so let's see. Right. Oh, I forgot to write down. If you multiply 2 times each one of these, you should get C6H10O4. That's the molecular formula, because we found out what the multiplier was. Or if we were going the other direction from molecular formula to empirical, we found out what the divisor is, which in this case is 2. Okay. So this is what a chemical reaction looks like. By convention, the reactants are always placed on the left-hand side. So in this case, this is ethanol, the drinking kind, and we're burning it, we're combusting it using oxygen. And the products then, and the products actually for for any of the hydrocarbons and carbohydrates, carbon, hydrogen, oxygen, or just carbon, hydrogen, the complete combustion in oxygen for these products is always carbon dioxide and water. Right? So if you need products that aren't given to you, if you're combusting a carbohydrate of this kind or a hydrocarbon without the oxygen, you'll always get carbon dioxide and water if the combustion is complete. If it's not, then you should be given the products. But in this case, the products are carbon dioxide and water. And then you have an arrow in between. Now later on, we'll use a double-headed arrow because in fact, reactions theoretically can go in reverse. In this case, we're showing you a single-headed arrow, and we're taking this ethanol combusted in oxygen to carbon dioxide and water. That's the end of the story, for simplicity's sake. All right. Now, in this case, the equation we say is balanced. How do we know it's balanced? We know it's balanced because the number of carbon atoms on the reactant side is equal to the number of carbon atoms on the product side. The number of hydrogen atoms on the reactant side is equal to the number of hydrogen atoms on the product side. And the number of hydrogen atoms on the reactant side is equal to the number of, did I say hydrogen? Oxygen. Carbon, hydrogen, oxygen. Each of the elements has the same number of elements on the reactant side and the product side. And we say that's balanced. And it also obeys the law of conservation of mass. Because if you have the same number of each element on both sides, then you have not created mass, you have not destroyed mass in the process. Now, this number that precedes an element, a molecule, a compound of any kind is called the coefficient. And the coefficient, when you go to balance an equation, this is the only number that you can change, the coefficient. Once you have written the compound correctly, right, that's why we spent so much time early on learning how to write compounds. So once you have written the compound correctly in the reactant side and the product side, those formulas are sacred. You don't touch the subscripts. I know there's a temptation just to make it balance. But if you change the subscripts, you've changed the products or the reactants or both. And then you don't have the same reaction. So once you've got the compounds written, don't touch the subscripts. The only way you can balance an equation is with coefficients. The other thing you may notice is this one doesn't have a coefficient. That's because if the coefficient is 1, we don't write it. If you've got the molecule there or the element there, there's at least one of them. And you only need a coefficient if there's 2 or more. The other thing we do is we try, at least for now, we try for whole numbers as coefficients. That's the ideal. If you stick with me long enough in this course and the next, you'll see that there are situations where fractional coefficients are valuable and useful. But we'll identify those. So for now, you try for whole number ratios for your coefficients and no fractions. Now, what does this mean? A balanced equation can mean one of 2 things. There's 1 molecule of ethanol plus 3 molecules of oxygen. And remember, oxygen is one of the diatomics. Remember the diatomics. Let's see, here we go. Hydrogen. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are the diatomics at normal atmospheric pressure and room temperature. So if you were to read a word problem that says ethanol is reacted with oxygen gas at standard temperature and pressure to produce carbon dioxide and water, you know that you have to write oxygen as O2. If you don't write it as O2, this equation will never balance. Right? That's why I emphasize learning the diatomics. You learn the symbols, yes, that's good. But you have to know which ones are diatomic. And those gases, well, most of them are gases. Those diatomics on the periodic table that I showed you and outlined in that special table where they were marked off in blue, those diatomics you need to know. So if I say we're reacting something with nitrogen gas, it's N2, not just N. Okay. The other caveat for balanced equations is a balanced equation is the ideal situation. This is the ideal ratio of reactants to products. What actually happens in a reaction is for another, a later topic in stoichiometry, where you have less than 100% efficiency. But the balanced equation as written is your starting point, and that's 100% efficient. You can also look at your balanced equation as ratios of moles. So let me back up. 1 mole of ethanol plus 3 moles of oxygen gas yields 2 moles of carbon dioxide and 3 moles of water. Okay? So it can either mean molecules or moles. Now, if you're going to do calculations, think of it in terms of moles. Let's see, what else can I say? Lest I forget to say it later, sometimes the balanced equation I'll just write the reactant side to make my point, has a parenthetical identifier following each one. In this case, I put a little L next to ethanol. At room temperature and pressure, ethanol is a liquid. That's what L stands for. At room temperature and pressure, oxygen is a gas. So I put in parentheses a G for gas. Now sometimes you can have different phases depending on the reaction conditions. And it may be important to identify which phases those are, particularly later when we do calculations. The other possibilities you could have are solid. Right? So if we had a reaction with calcium carbonate, limestone, it's a solid. Or you can have reactions in aqueous solution, in which case we would follow with AQ. Now there are a number of other parenthetical identifiers that you can assign, but these are the ones that we're going to focus on. We won't use any of the others. Okay, I guess I better move along if I'm going to finish this chapter. Okay, so these are the steps in balancing an equation, and they're just there for your guidance later. I think it's better just to show you how it's done. Okay, I will make a point though that your textbook and most chemistry textbooks gloss over the process of balancing equations. That seems strange to me because a balanced equation is vital to any investigation in chemical reactions. And they gloss over it by saying you balance the equation by inspection, right? But they don't tell you how to do it. So, in my opinion, the authors always evade the questions. So I'm going to show you how, give you some tips, some methods to use, and the more you do it, the more intuitive it will become. Because there's more than one way to balance an equation. All right, so what I like to do is write out the equation without the coefficients. Be sure the compounds are written correctly. For this one, C6H12O6 is glucose, right? Same stuff that circulates in your blood and supplies energy to all your cells. Now this, of course, is oxygen, and that combustion, whether it's fast in a flame or slow inside your cells, stepwise, produces carbon dioxide and water. So you want to write all your compounds and elements correctly. Get those down first. Then set up underneath your equation that's not balanced yet, set up underneath it a table of the elements on both the reactant and the product sides. And I'll show you what I mean by that first. I'll give you these others as we go. So let's see. So here's an example. So what do we have? We have ammonium phosphate, which is written correctly. Phosphate is a polyatomic ion with a 3- charge. Ammonium is a +1 charge, so we need 3 of them. So 3 pluses balances 1, 3-. Calcium is 2+ because it's an alkaline earth. They're all 2+ charge. Chloride is from the halogens. It's a -1 charge, so you need 2 minuses to balance a 2+, and so forth. So you make sure all of your compounds are written correctly. Then you put them on the correct side of the equation. These are reactants, those are products. Now below them, you set up what are you going to be balancing, right? You could set it up with each element separately, like nitrogen, hydrogen, phosphorus, oxygen, calcium, chlorine. That's possible. But if you do that, and you don't need to, then you're adding a lot of work. But under what circumstances would you not need to write separate elements? In this case, this is one of the hints, the tricks that I give you. If you have a polyatomic ion on the reactant side, and the polyatomic ion shows up on the product side with no, what's the word, disproportionation. It's not separated in the process. In other words, if you have ammonium over here and ammonium there, but the nitrogen in there, for instance, does not appear somewhere else, then you know that molecule is intact, both sides of the equation. If the ammonium is both sides of the equation, you can use it as a balancing group. And that simplifies the process enormously. The same thing for phosphate. Phosphate's over here, and nowhere else. Then it's also a balancing group. So that's one trick to simplify. Calcium has to be taken as an element. Chlorine has to be taken as an element. Right? So you have these. Now, what are the initial amounts of each one? The initial amounts on this side, you count them up. How many ammoniums do you have? You have 3. Right? How many phosphates do you have? Just 1, right? Right? This subscript means that there are 3 ammoniums. How many calciums do you have? You're starting off with 1. And chlorines, you're starting off with 2. Okay? How many do you have on the product side? Let's see. Yeah. Product side. Well, Look at the ammoniums. You only got 1 on that side. See, so you know that they're not balanced yet, because there's 3 on this side and 1 on that side. That's a dead giveaway. It's not balanced. You have 2 phosphates on the product side. You have 3 calciums, and you have 1 chlorine. All right. The beauty to setting up this budgeting scheme is that at a glance, you can see that your equation is not balanced, and when it is balanced, it'll be obvious. You'll have the same numbers in the final. I put this in the final column here, but when you actually do it on the board, you can just cross these out and put the new value in. And the only reason I'm not doing it on the board now is because it'd take too much time, and I've already got it set up in this animation. Okay, so now you've got your initial tally. Where do you start? If there's no obvious place to start, and you'll learn that from experience, then just start at the top, because you'll eventually get there. It just may take you more steps doing it that way than if you have some intuition about where a good place to start would be. So let me see, do I have any intuitions here? I'm going to start with calcium, okay? And that's fine. You can start with ammonium if you want to, but I'm going to start with calcium. Step 1, and that's what this little red number is. Step 1, calcium, put a 3 there. And that means this one changes to 3. So we now have our calciums balanced. But when you put a coefficient in front of that compound, what does it do to the chlorines? It also changes the number of chlorines. Okay, so now we have 6 chlorines. Well, that's okay, because we weren't balanced in chlorines to begin with. So the next step is, let's go to chlorines. All right, and to change the chlorines, we need a coefficient in front of this molecule, which you may guess, once we put a number in front of that one, it'll change the ammonias also. So we need 6 chlorines. There's our 6 coefficient. 6 times 1 chlorine is 6 chlorines. Okay, so let's make that change in our budget. Well, we're going to do the ammonias as well. We've got 6 ammonias and 6 chlorines. Remember, this is a polyatomic ion, and we're using it as a balancing group, which means you have to count it as a unit. Right? So 6 units of ammonium. Don't think of it, when you're using this method, don't think of this as 6 nitrogens and 24 hydrogens. Think of it as 6 ammoniums. Okay, now that we've got the calciums and the chlorines balanced, we've changed the ammoniums, so let's go back on the other side. And we need 2 times 3 will give us 6 ammoniums on the reactant side. Okay? So what else is that? That has to also change the phosphates. Right? So 2 times PO4 is 2 PO4s. Right? So we got 2 PO4s here. How many we got on this side? We got 2. So let's just back up and take another tally. So we've got 6 here, 6 here, 2 there, 2 there, 3, 3, 6, 6. We're balanced. And if you keep up with your tallies like this, you know you're balanced immediately. There's no guesswork. Okay, any questions so far? Well, I wet my whistle. Okay, this showed you one of the tricks where you use polyatomic ions as your balancing group if the polyatomic appears on both sides of the arrow and is not divided in any way in the process. Okay. This just drives home the point. Which one of these is the best? Well, let's see. you have to ask yourself first, are they balanced? Right? There's one calcium, 2 oxygens, 3 carbons, 2 plus 1 is 3. So that's balanced. And if you go down through all of them, you'll see that they're all balanced. Well, they're not all balanced. I think the last one is not balanced. 4 oxygen, let's see, 10 carbons. 2, well, that is balanced. 3 carbons. Yeah, it looks like they're all balanced. But the one we prefer is the simplest whole number ratio. And let's see. Oh, I just skipped right by it. Does anybody see what I did wrong? This one is written wrong. Notice? Calcium is a 2 plus ion, oxygen is a 2 minus ion, so you only need 1 of each. Right? So CaO2 is written incorrectly. So that one's out immediately. The rest of them are different ratio numbers. And we want the simplest whole number, which is this one. Now that's valid. That's valid also. But the best one is the first one. Okay. So, well, I already gave you the answer. Which of the following are true concerning balanced equations? Atoms are neither created nor destroyed. Conservation of mass. The number of molecules is conserved.
As women, we place our trust in our hygiene.
Number of molecules can be wildly different because those coefficients are the only things that are important. And the coefficients tell you how many molecules there are. So the number of molecules is not conserved. Coefficients tell you how much mass of each substance you have? No. Coefficients only tell you the numbers of, either the numbers of atoms and molecules or the numbers of moles. Right? So an equation only relates, on the surface, it only relates numbers to numbers, whether it's numbers of atoms and molecules, a number of atoms of elements on either side, or number of moles. That's the only thing that it relates when balanced. Now you can use it to relate masses, but that's a procedure I'll have to show you. The coefficients indicate the mass ratios? No, we just said that was wrong. The sum of the coefficients on the reactant side equals the sum of the coefficients on the product side? No. That's another way of saying that molecules are conserved. So 1, 4, and 5 are all wrong for the same reason. Okay. These are just reminders of everything that I've told you so far. The coefficients can be fractions, but for now, let's make them whole number integers. Make them integers only. We'll find out when fractions are useful and then incorporate those into our portfolio. Okay, let's see. I didn't show, okay. There are a couple of tricks that I wasn't able to show you, and I think I'll save them. Let me call your attention to them first. Let's back up. Let's see, where am I? Can I go backwards? Yeah. Let me go back and call your attention to those hints. Come on. Here we go. Okay. When you're balancing an equation, in addition to noticing whether you have polyatomic ions that can be used as balancing groups, look for elements that are by themselves. Here, oxygen is by itself. Always save those till last. And that only makes sense. Remember, if you change the coefficient in a molecule or in a compound, you're going to change everything in the compound, which means you got to deal with it other places in the equation. But if you change a coefficient on an element, you only change that one element. So save it to last, right? Balance everything else, then go back to oxygen. As a corollary to that, you may also find it useful to save water till next to the last, right before oxygen. I think, well, right before the element. It just seems to work out better that way. Let's see, what else? In balancing an equation, sometimes it's more efficient to use a fraction as a coefficient. Now, I didn't show you an example of that, but sometimes to get the right number, say you save oxygen till last. And in this case, we need 25 oxygens, right? Because we have 16 here, and we have 9 here, which means 25 oxygens. So how do you get 25 oxygens on the reactant side? Well, 25 halves will give you 25 oxygen atoms, right? Because there are 2 in each one. If you take a half of that molecule, then you got 1 oxygen times 25 is 25 oxygens. Okay, so that balances the equation as an intermediate step. Then how do you get rid of that half if you want to have whole numbers only? Well, you just multiply the whole equation through by 2. And that 2 cancels this 2 in the denominator. But it also multiplies everything else by 2. So now you have 2 of these. You have 25 of those because you got rid of the half. You have 2 times 8 is 16 here. 2 times 9 is 18 there. So that's an intermediate step. You'll find that if this is a hydrocarbon, CH18 is one. It's octane, right? Same thing as in your gas tank. Any of the hydrocarbons that you combust are going to use this process, except for methane. Methane's unique. But anything 2 carbons or bigger, you'll always have this problem. So that's a good place to use it. It happens other places too, but this is just one that I've noticed all hydrocarbons are that way. Okay, those are the 2 rules that I forgot to include. Okay, so let's move on. Let's see. Okay. So now, the balanced equations are balanced in terms of numbers of atoms or numbers of moles. But we don't have the ability to measure them directly in any of our laboratories. We always measure in volumes, in lengths, in areas, masses, even concentrations of solutions. We measure in those terms. We don't measure actual numbers of atoms. So we need a way that we can use things that we do measure to relate to things that we can't measure, which is the balanced equation. So in stoichiometric calculations, we're going to learn how to relate. First, we're going to learn how to relate masses of reacting chemicals to each other and determine how much mass is produced in the products. Okay? And the key to conversions, because we're going to have to do conversions, right? We got to go from masses to moles before you can use a balanced equation. Then we need molar mass. So you got to remember and be proficient at calculating molar masses. Right? So here are steps again that I've given you, and we need to go through an example in order to, let's see. Well, these are also steps in a flowchart format. If you like that, that's fine. But I'm going to show you an example. So I'm going to do this one on the board because I don't have it as neatly provided in an animation. So we have P4, which is what? Phosphorus. So we have P4. And let's see, let me bring it down just a little bit. P4. And that's a solid. And then oxygen, gas. And we have P2O5. And that should be also a solid. Okay. You'll notice that this equation is already balanced for you. 4 phosphorus on this side, 2 times 2 is 4 phosphorus on that side, 2 times 5 is 10 oxygens in the reactants, and 2 times 5 is 10 oxygens in the products. So we've been kind enough for this demonstration to already balance the equation. But that's the first thing you, actually the second thing you do. First thing you do is be sure all your compounds are written correctly. All your elements are written correctly. Then you balance the equation. Then you can move to stoichiometry. So what are we given? We're given the balanced equation. We're also given 6.25 grams of phosphorus. Okay? And we're told that it's burned in an oxygen atmosphere. What mass of oxygen does it combine with? So how much oxygen is required to convert that many grams of phosphorus into products? Right? So we want to know that's grams, not gas. How many grams of oxygen are required to use up this? All right, here's a point that I want to make. When you're only told this and you're asked a question like that, oxygen is in excess. There's plenty of it. You'll never run out. So you can use up all of this with as much oxygen as required. All right, it's not limited. If we were given amounts of each one, then you would have to assume that one of them is probably limiting. And I'll show you how to deal with that. Yeah, I'll have to wait till, I'm not even finished with chapter 3 yet. So we're going to have to move along. What I may do, let me see. Let me see just how much I've got left to go. I may, yeah. I still have to talk about limiting reactants. Okay, so in the interest of time, if you have to leave at the end in 1 minute, go ahead. I'm going to keep talking and finish this chapter. And then I'll post a video and you can pick up the rest of it. And if you have any questions, just pop in during my office hours and ask me anything. I've got office hours on Mondays, Tuesdays, and Wednesdays. Or if you can't meet office hours, just let me know and we'll set up a private session. But I'm going to continue talking and recording if you have to leave. Okay. So here we have a balanced equation. We're given 6.25 grams of phosphorus, and we want to know how much oxygen is required to consume all of that phosphorus and produce product. Okay, so we've got correctly written elements and compounds, we've got a balanced equation, we've got our given information. Now what do we do with it? All right, you can't go anywhere in an equation until you got moles, right? If you've only got grams, if you've only got a solution concentration, got anything but moles, you can't move. You're stuck. So we've got to convert this to moles before we can go anywhere in this equation. And we want to go from here to there, right? So it's like a great divide. You can't get across that wall unless you're moles. So what do we need here? We need to know the molar mass of P4, right? So we look up phosphorus in our periodic table. It's off frame now, but look it up. 30.97 times 4. Okay? $123.88 grams per mole. So now we have a conversion factor. We can use this conversion factor to convert that many grams into its equivalent number of moles. So how do you know how to use it? Well, you start with this, right? And you want to end up with moles, right? So that means this has to go on top and this has to go on the bottom, right? This is in the numerator, so it cancels and leaves us there. So 123.88 grams per mole. So that means you divide 123.8 into 6.25 to give you the number of moles of P4. So 6.25, and I'm going to divide it in there. 5.045 times 10 to the minus 2 moles. That's how much P4 we have. Okay? Now, since I'm limited on space, I'm going to have to do some erasing and rewriting. Okay, so now we know that we have 5.045 times 10 to the minus 2 moles of P4. All right. Remember early on I said a lot of chemistry is just converting units, conversion factors. This is one of those examples. We used one conversion factor to get to there. Now we're going to use another one to get over here. Because now that we're moles, we can go there. The question is, what's the conversion factor? Well, where do we want to go? Well, we want to go to grams, but we can't get there yet, right? We can go from moles to moles. Yeah, we can go from moles to moles because we have a balanced equation. And I'll show you how that works. The ratio of moles of phosphorus to moles of oxygen is 1 P4 for every 5 O2s. That's the ratio, 1 to 5. So we have one of these for every 5 of these. Okay, there's your conversion factor. In fact, what we're saying is that 1 is equal to that 5. That 1 is equal to that 5. That makes our conversion factor. So this one cancels like that. And now, when we multiply 5 times that, we end up with moles of oxygen. So 5 times this, I think I still got it in my calculator, is 2.523 times 10 to the minus 1 moles of oxygen. Yep. So that's how we converted from this many moles of that, so grams of that to moles of that, moles of this to moles of that. Now, since the question is mass, we've got to convert this back into grams, right? So we need a conversion factor for oxygen. See anything familiar? Grams per mole, molar mass of oxygen. So what's the molar mass of oxygen? Well, rounded off to 2 decimal places, the molar mass of O is 16. But we've got 2 of them. So the molar mass of O2 is 32. So 32 times that value is 8.07 rounded off to 2 places. That's how much oxygen we need to completely consume 6.25 grams of phosphorus. Okay? That's stoichiometric calculation in a nutshell. Let's see if I'm going to need that again. No, okay. All right. Let's make some room. This one is a little more involved. So the problem is we have two different reactions and we are artificially relating them. First, we need the balanced equation. All right. So we're going to react methane in oxygen, air, and produce carbon dioxide and water. Okay. So that's simple enough. Ammonia is reacted with oxygen to give us nitrogen monoxide and water. So you're given the products. And that's the case. In most cases, you will be given the products. There are special cases where you should be able to deduce the products. And I'll point those out, and they'll come later, not in these chapters, or at least not in this chapter. So let's write the balanced equations. Okay, so we would write methane, oxygen, carbon dioxide, water, and then balance the equation. All right, that's why these coefficients are in here, and you can check it out for yourself and see that we have same number of atoms of each element on both sides. And we'll do the same thing with ammonia. And there we have our balanced equation for that one. So that's part number one, balanced equations with correctly written compounds and elements. Remember the diatomics, don't forget the diatomics. Okay, now part two is, the question is, what mass of ammonia would produce the same amount of water as 1 gram of methane? Okay, so let's go back, because we're going to need our balanced equations. Let's go, all right, here, here. There we go. Okay, so we need our balanced equations, methane, oxygen, methane. Let's see, to water. Yep. And then we're going to relate that to ammonia. You know, that's written wrong. Look at there. That's written NH4, it should be NH3. Right? So that equation is not properly balanced. Hold on a second. All right, this is the wrong slide set. I had corrected that in another slide set. So hold on just a second. I'm going to stop this share and get the correct one in there. Let me pause the recording. I'll be right back in a second. Okay, I'm back. Now I'm gonna share the correct PowerPoint. I think it's this one. Okay, slideshow. Where's my slideshow? And slideshow. There we go. There. Now, this is properly balanced. So we have 4 ammonias, 5 oxygens, 4 nitrogen monoxide, and 6 water. Now, these 2 reactions are independent of one another. We are artificially relating them by this next statement. What mass of ammonia, right? What mass of ammonia would produce the same amount of water as 1 gram of methane? So if we take 1 gram of methane, excuse me, that's 2 decimal places. 1 gram of methane and make water, how much ammonia would it take to make the same amount of water? Right? So what are we actually wanting to do? We need to find out how much of this is produced. And to do that, we have to follow this one to its completion and take that same amount and use it down here. Okay? So that's the thought process. So how do we do that? Well, we need so much water over here. We've got to find that unknown before we can go to the next step. All right, so let's see. Did I do any calculations here? I've got it on another. In fact, I do. Okay. So let me take advantage of the problems already appearing in the slides. Write out the balanced equations. There we go. Now, how do we know how much water is produced in the reaction of 1 gram of methane? And we have to assume also that there's excess oxygen. There's plenty of oxygen. So this will save me the process of writing it on the board, which would take a lot longer. And if you need to, you can pause the slides or pause the video and you can follow in steps. So we need here the molar mass of methane, right? Because we can't go anywhere with mass of methane. We have to make moles out of it before we can move over to the water side, right? Can't go over here unless we're moles. So we convert this 1 gram into moles with its molar mass. So we know that we have 6.23 times 10 to the minus 2 moles of methane. And then we're going to convert that into how many moles of water. So we need a conversion factor, right? So moles of methane, which is this, cancels and leaves us with moles of water. And in standard notation, I've got 0.1246 moles of water. Now, the way the question was asked, what mass of ammonia would produce the same amount of water? It says the same amount of water. It didn't say the same mass of water, but if we know the amount, which is moles of water, it's the same thing as saying mass. If the problem had said to produce the same amount, same mass of water, we still wouldn't need to convert it to mass because the amount would be the same, whether it's moles or mass. So you can save yourself a step by just taking this one, translating it to this problem. Now this is the number of moles of water that we want to produce down here, right? So there's the amount of water that we produce, and we're putting it in this equation now, in the second equation. And we're converting moles of water to moles of ammonia because we have to go from here over here. And the ratio is for every 6 moles of water, there, we have 4 moles of ammonia, there. So the conversion factor cancels water and leaves us with ammonia, 8.31 times 10 to the minus 2 moles of ammonia. All right, so the question is mass of ammonia. So we're not done yet. We know how many moles of ammonia that will be produced as a consequence of this calculation. We just need the molar mass of ammonia, right? So 14.01 plus 3.03 for 3 hydrogens gives us 18.05. Wait a minute, that's not right. No, that's not right. 14.01 for 1 nitrogen and 3.03. That's an error, right? So let's do the correct calculation. Where's my calculator? Here it is. So instead of 18.05, we need 17.04 times 8.31 times 10 to the minus 2, 1.42. So this should be 1.42 grams. There. Okay? Now, before I post this video, I will make the corrections in the PowerPoints so that when you actually, if you want to look at the PowerPoint in parallel with the video, you'll have the right slides in that case. So I'll make all those corrections first and post both the PowerPoint slides and the video at the same time. Okay, the last topic that we want to cover is limiting reactants. Actually, this is next to the last, but this is a major topic. Whenever you have 2 or more reactants that are, and we're going to simplify things, we say we only have 2 reactants. If you're given amounts of each reactant, you may assume that one of them is limiting. What do I mean by limiting? Limiting reactant is the one that runs out first. That limits the reaction, because when one of the reactants runs out, the reaction stops, right? Without one of the reactants, you can't go any further. So the limiting reactant is the one that runs out first. And the one that doesn't run out is excess. So how do we tell which is limiting? Because up to now, we've been assuming that either one was in excess or the ratios of reactant to product was stoichiometric. When we say stoichiometric, that means they're exactly the right amount of each reactant, where both of them are consumed at exactly the same time to convert to products. So this is a stoichiometric mixture. Right? Here we have 1 nitrogen molecule, 3 hydrogen molecules produce 2 ammonia molecules. Right, so what does that look like? Well, nitrogen is diatomic, right? So here's the big blue nitrogen. Hydrogen is diatomic. Here's the little pearly hydrogens. And here's the ammonia with 1 nitrogen and 3 hydrogens, just like that. So in the reactant side, if it's stoichiometric, you've got exactly 1 nitrogen and 3 hydrogens to react together. And notice that each amount is paired up, so that there's none left, and the products give you 2 ammonias for each one of those groupings. That's stoichiometric. In reality, in a lab where you actually have to measure out your reactants, that never happens. This is all theoretical. If you actually measure out reactants, and you don't plan on one of them being in excess, if you actually measure them both out and think that you can get them properly measured so that they are stoichiometric mixture, then you're fooling yourself. It never happens. Why? Experimental error, measurement errors. You can never measure exactly as much because you cannot get down to exactly atomic molecular level, right? If you could, then you could separate them out, group them, and be stoichiometric. But translating macroscopic measurements to the microscopic world, you will never get a stoichiometric mixture. So we have to deal with it. How do we deal with it? Well, the concept of the limiting reactant is how we deal with it. In this example, hydrogen is limiting. How do I know? Well, on the reactant side, at the molecular level, we see that these are properly paired, those are paired, and those are paired, but these two nitrogens are left over. They're excess because they had no hydrogens to bond with. And as a consequence, they're still here on the product side, right? They're excess. The one that ran out was hydrogen. Okay, so in this case, the limiting reactant that ran out first was hydrogen. And this is an exercise in which of the following reactant mixtures could produce the greatest amount of product. So for this reaction where you have hydrogen burned with oxygen to use water, look at it this way. If you have 2 moles of hydrogen and 2 moles of oxygen, which one runs out first? 2 moles is what you would need for hydrogen here. But you only need 1 mole of oxygen, right? So you've got 2 moles of oxygen, you only need 1, that means oxygen is in excess, and automatically the other one is limiting. So hydrogen is limiting. Oops. Well, if you go through each one of these steps, you find out that for every occasion, they each produce the same amount of product. Why? Because with 2 moles of hydrogen in the first example, the limiting reactant determines how much product can be produced. So 2 moles of hydrogen produces 2 moles of water. Doesn't matter how much oxygen, once you're excess. Here, 2 moles of hydrogen produce 2 moles of water because we have even more excess oxygen. In this one, we have 2 moles of hydrogen and 1 mole of oxygen. That is stoichiometric, which produces 2 moles of water, the same as A and B. And for D, we have 1 mole of oxygen, 3 moles of hydrogen, which means, in this case, hydrogen is in excess and oxygen is limiting. But the ratio of 1 mole of oxygen to 2 moles of water with hydrogen in excess produces exactly the same amount of water as A, B, and C. So that's why each produces the same amount of product. All right? In order to determine which one in the real world is limiting, you can't just add up the totals and determine which one is limiting, because most often you have reactants given you in terms of mass or volume, say if they're all gases, or if they're solutions, they're given to you in so many milliliters of a concentration of solution, right? So what you have to do is do a what if calculation. So what we do is we take each one of the reactants. Say we have reactant A, reactant B produces C. Okay. Say we have little a grams of this one, little b grams of that one. All right. So how do you tell which one is limiting? Well, you assume excess of the other. We say A, we have this many grams, and we say there's plenty of B. Just suppose, how much of C would A produce? So A would produce a certain amount of C, call it C1. Let's call it AC, AC1. Then you go back and say, let's say A is in excess and B is limited. How much would it produce? So we take all of this and make C out of it. So we say BC amount. Okay, so you have two amounts, right? And they won't be equal unless they're stoichiometric. If they're stoichiometric, they'll be equal. If they're not stoichiometric, then one of them is limiting, and you know which one is limiting by which one produces the least amount of product. So let's say A is limiting. AC product will be less than BC product. Okay? That's how you tell which one's limiting. Which one produces the least amount of product if all of it is reacted. Okay. So I don't have any examples here in the slides as given. So I think what we're going to do in the interest of time is go into the review document, into the problems that are taken from chapter 3, and let me verify that. I want to verify that we're subdivided that way. Yes, the review document is subdivided into chapter 3 problems followed by chapter 4 problems. So with this chapter 3 discussion completed, go into chapter 3 and attempt a limiting reaction problem, and then have right next to it have how the problem is worked in my handwriting. Remember that extra document. Have that one there and follow along as you go, and just use one of mine as an example and do a limiting reaction calculation. And then we'll talk about it at our next meeting, or if you want to, we can wait till the review session. We can talk about it then. Now, the last thing we have is percent yield. So how do we calculate percent yield? Very simple. You take the amount of product that you actually produce in a chemical reaction with, under given conditions, certain amount of reactant, certain amount of product, and you calculate the actual yield, how much of the product is produced. And then you go through your calculations, theoretical, even if it's a limiting reactant, you know theoretically how much you should produce. Take the limiting reactant, and that will tell you how much of the product is theoretically available. And then you just ratio the actual yield to the theoretical yield, and that gives you a percent yield. Now, in the real world, percent yield will always be less than 100. Always. If you've got a very efficient process, it may be a high yield, 90% or more, maybe. Or it could be a very low yield. And that's what businesses pay chemical engineers to determine. How can we increase the percent yield of our output? How much product can we produce for the input that maximizes profits? Right? So the higher percent yield that you as an engineer can produce, the happier your bosses will be. But you need to know what those values are, otherwise you can't improve on them. So the calculation of percent yield is something that's done routinely in industry. Okay, here's an example. Oh, we may be able to, yeah, okay. So this problem is going to incorporate limiting reactant and percent yield. So we're going to do the whole ball of wax in one problem. Right, good, good, good. I'm glad we have that opportunity. So let me be sure. And I need to move this over a little bit more. Let's see. There we go. Okay. Now for this problem, we're given the balanced equation with the arrow that's out of position. P4, the same phosphorus we used before, is reacted with fluorine gas. Right, so this is a toxic reaction. You want to conduct this under in a safe environment because it's very energetic, and the fluorine gas itself is toxic. So in your reactor, you will have so much P4 reacting with fluorine gas to produce PF3 gas. And PF3 is also toxic. So it's a good thing that we're doing this on paper and not in the real world. All right, the question is, well, let's write the equation first. And trust me, it's balanced. So P4 plus gas yields, and I'm going to write the product over here. There we go. Spread it out. The question is, what mass of P4 is needed to produce 85 grams of PF3? That's the first bit of information. The question is, what mass of P4? So that's what we want to know. What mass of P4 is needed to produce 85 grams of PF3? Right? 85 grams of PF3, except the fly in the ointment is the reaction is only 64.9% yield. Okay? So there, you're given everything. So for every 100 grams of theoretical production, you only get 64.9% actual production. Now, how can we use that? Well, we know that we're going to have to go from here back over there, right? So we have to produce something over here in moles, converted, then go back over here to moles, converted, and then convert that to mass. But we don't know what this is yet because this is actual yield with that efficiency, which means this is the actual part of the equation. So what do I mean here? Remember, percent yield is equal to actual divided by theoretical times 100. Right? So we know actual is what we want, right? How much do we have to start with to get an actual amount with that yield? So the percent yield is 64.9%. The actual we want is 85 grams. And the theoretical is unknown. Let's make it a different, not an X. Let's make it let's make it T for theoretical. So there's our equation with one unknown. You can solve for it. But you had to set it up correctly in order to identify the calculation that's required. So this calculation, we put in the right values here. This is actual. That's what we want to get, our actual amount. But we need to calculate theoretical because this equation stands by itself as theoretical only. Right? This is all stoichiometric. So we need to calculate what is the theoretical amount before we can go back to the P4 amount. So we solve for this one, and that means T equals 85 divided by 64.9 times 100. Right? So let's just do that calculation. 85, 64.9, 100, 130.97. Of PF3. So that's the amount that we need to use in here, not the 85, but we need to use this one in order to go back to here. Because this is all theoretical. That's actual. Right? So we have 130.97 grams of PF3. Now what do we need to do? We can't go anywhere in that equation unless we're moles, right? So we need molar mass of this. And convert this PF3 grams moles. Right? Grams of PF3 cancel. So what's the molar mass of PF3? Well, look on your chart. Phosphorus, 30.97. We need 3 fluorines. Fluorine is 19.00. So I get 87.97. 87.97 grams per mole. We divide that value into 130.97 because this is in the denominator and that's in the numerator. I get 1.49. 1.488 moles of PF3. Now we can go back over here because of what ratio? If we have 1.488 moles of PF3 and we want to convert it to moles of P4, we need P4 on top, PF3 on the bottom. Moles of P4, 1. Moles of PF3, 4. So we divide 4 into that value. And we get 0.372. 0.372 moles of P4. Okay? We're almost there. We know how many moles of this we need to get where we want to go. Now we need to convert it to grams. So let's take 0.372 moles of P4. All right, moles on the bottom, grams on the top. Grams and moles as a quotient, automatically you should think molar mass. P4. So P is 30.97 times 4. 123.88. 123.88 times this value yields 4.61 grams of P4. Okay, so I know that's a lot of steps. So you have to approach it logically, and you have to know what you can and can't do when. So if we react 4.61 grams of P4 with excess fluorine, we're going to produce, well, actually, I said we were going to determine limiting reactant, but we didn't do it because F2 is excess. But if we react this with fluorine, we're going to get 85 grams of PF3. Now, we know that if it were 100%, we would get, let's see, well, I lost my figure. We would get a lot more than that. But we know we have to start with this, if we know the efficiency to be that, to get this amount, actual amount. All right, so what happened to the rest of it? Right? What happened to the rest of it? Well, possibilities, all of this didn't react. Right? There may have been a reverse reaction competing with it. That happens a lot. Or with our process and our equipment, maybe all of it was converted to PF3, but that's a gas and we got a leak that we don't know about. You know, anything is possible. Of course, if you're leaking that into the environment, you're probably going to injure or kill a worker or two in the process, and you'll pretty soon you'll know you have a leak. But collection efficiency is one possibility. All right, so like I said before, go to your review document and try a problem that's asking you to determine which reactant is limiting, and follow along with the way I work the problem so that you can see how it's done. I've described how it's done, but that's no substitute for actually doing it. And there are several of them in there, I know there are. So you'll get lots of practice as long as you work all the problems in the review document. Okay, there are the steps. Oh, okay, here we go. 130.97 grams is what we should have produced from that many grams of P4. But we only got 85. So we lost a lot somewhere. Either it wasn't converted or we lost something in the process. Competing reactions. You know, it could have ended up as something not PF3. Right? It could have gone to some other product. That happens too. Okay. So oops, I made a mistake. Yep, I did. My decimal's in the wrong place. There we go. 46.1 grams of P4 are required. Okay, that's the end of chapter 3. And I've done enough damage for today, so we'll stop the share. And